Let's do another example. This one, in addition to ones and zeros, I want to put something else too, and then introduce the concept of don't cares. When we look at a map like this, okay, a map like this, we put ones here. Let's say, for example, here and here. We are talking about a function that has to be 1 when A is 0, B is 0, C is 0, D is 0. Okay, like this. It has to be 0 here, it has to be 1 here, it has to be 1 here, and 0 elsewhere. Okay, what if there were certain values we didn't really care about? Okay, let's think of a function that maybe if the inputs are, let's look at numbers between 0 and 9. If the inputs are above 9, 10, 11, 12, 13, 14, we don't really care what the output is, or the inputs are not supposed to happen at all. If that's the situation, when I'm drawing my truth table, based on that, I'm coming up with my Karnaugh map, and I'm putting ones and zeros. What do I do for the values for which I don't really care? Do I put zeros, or do I put ones? If I put zeros, what happens is, so get this, if I put zeros, okay, if I put zeros, well, let's go into this map. Okay, if I put zeros for those that I don't care, I'm fine, but then I will be I will have ones that may not be easily mapped with other ones close to them. On the other hand, if I put ones in the places I don't care, I will have a lot of ones that I have to cover which I don't really need it to cover. So what do I do? Look at this function here. This function has a 1 in position 0, 0, 0, 0, has a 1 in position 0, 0, 1, 1, okay, and has a 1 in position 0, 1, 1, 0, has a 1 in position 1, 0, 0, 1, and then don't cares elsewhere. Actually, this is a circuit that says this. The input is a BCD number. BCD means 0 to 9. Okay? A, B, C, D. And if the output, if the input is divisible by 3, or if it's 0, then the output becomes 1. Okay? If it's divisible by 3. Or if it's 0. Okay? Well, 0 may be divisible by 3 too, right? 0 divided by 3 is 0. So if the inputs are 0, 3, 6, 9, the output is 1. What if it's above 9? Well, above 9 is not the BCD number, is not a single digit. And therefore, 10, 11, 12, 13, and 14, and 15, we don't really care. Okay? What do I do for the Karnaugh map for this circuit? Let's play with two scenarios here. I can put all ones or all zeros. For the outputs, I don't care. Or for the input combinations that will never happen, I will put all zeros. If I put all zeros, and if I were to map this, I would map this just by itself. I would map this just by itself. Okay, let me show my zeros a little bit smaller so that they don't get confused with the maps there. Okay, and I map this just by itself. What would this come out to? This becomes A bar, B bar, C bar, D bar, ORed with A bar, B bar, C, D, ORed with A, B bar, C, D bar, C bar, D. Okay? If you were to build this, you need big 4 input gates and the 3 input gate for the output. So maybe I did, oh, there is another one over here. So I also need A bar, B, C, D bar. Okay, so maybe I don't like this, but let's do something else now. Let's, instead of using zeros for the don't cares, let's use ones for the don't cares. If I use a 1 for these don't cares, this is what I end up with. Okay, now let's look at the maps. Well, the maps look a little bit better, but see, here I have this one that maps with this new one. Here I have these 4 ones are mapping together. Okay, this one maps just by itself. This one maps with the one next to it. But then I have these 2 ones I have to map. These 2 ones I have to map too. Okay? If I want to write everything, that becomes A bar, B bar, C bar, D bar. Ordered with B bar, C, D. Ordered with B, C, D bar. Ordered with A, D. Ordered with A, B bar, C. Okay? Well, the problem with this is true that, for example, this one here helped me with the with enlarging my circle, so I dropped the variable. But then some of these ones, like this one here, were don't care, but I was obliged to cover them anyway. And this one gave me a lot of ones that couldn't be mapped next to each other at all. So what do? I don't like to consider them as zeros. I don't like to consider them as ones either. So let's consider them as something else. This time I'm going to call them don't cares. I really don't care about the value that they have. And therefore, I leave my ones and zeros as they are. And for the values I don't have, or I don't care, or the input combinations that are not supposed to happen, I put dashes or don't cares. Okay? In mapping, if they can help me create larger maps, I use them. That's it. If they don't help me create larger maps, I just ignore them. Okay, so let's do this. I look at this one over here and find 3 dashes next to it, and I find that, okay, this is a good map. I'm gonna use this, and I'm gonna treat the 3 dashes as ones, and therefore this becomes A, D. I'm gonna look at these and say, well, this and the dash beside it are good, and that's gonna give me B, C, D bar. I have another map here which maps with this one over here, and this one turns into B bar, C, D. Okay, and finally this one doesn't help anyway, and then this one is A bar, B bar, C bar, D bar. Okay, just write these a little bit more compact. So my function becomes this. Now compare this with this. 1, 2, 3, 4. 4 variable product terms. That means big NAND gates. This one, 1, 2, 3, 4, 5, it doesn't have four, it has one more product term, but it's smaller. But then this one is the ideal situation. It has four product terms, two of them are three variable product terms. One of them is a two variable, only one of them is a four variable product term. If I want to just calculate the number of gates, the number of transistors, this has the most. And let's see, let's do this. Not counting the inverters, this has 8, 8, 8, 8. That's 32. And then 1, 2, 3, 4. That's another 8. So that's 40 transistors altogether, not counting the inverters. And if I were to do this using NAND gates, this one, 1, 2, 3, 4, 5 terms. That means a 10 transistor NAND gate in front, plus 6, 6, 6, 18, and 8, that's 26, and then 4 here, that's 30. Okay. So that's also 40. How about this? 8 for this term. 8 plus 4 plus 6 plus 6 for these two, and then the 4 input gate for putting them all together, that's 8. So that becomes 12, 20, 28, 30. 2 gates for this realization. Therefore, using don't cares as don't cares, and sometimes taking them as zeros, sometimes taking them as ones, is the most appropriate way of treating them, so that I can reduce the number of transistors in my circuit. What I have shown you so far is I've shown you Karnaugh Maps, and in the Karnaugh Maps I have tried to have ones and zeros and try to map those ones and zeros, but then I haven't shown you a systematic way of selecting the maps. Okay, I'm going to talk about some definitions here. Implicants. Implicant is a let's look at a 4 variable map. Okay. If any term becoming a 1 can turn my function to a 1, that term is the implicant of my function. If A, B, C bar, D bar, because there is a 1 here, if this becomes a 1, my function becomes a 1, and therefore this is an implicant. A, B, C bar, D, if this becomes a 1, this is this one here, my function becomes a 1, therefore this is an implicant. If the combination of these two, A, B, C bar, becomes a 1, so will my function, and therefore this is an implicant. If any of these become a 1, so will my function. Let's write down A bar, B bar, C, D. Okay, that's an implicant. A bar, B, C, D, that's an implicant. A bar, B bar, C, D bar, that's an implicant. A bar, B, C, D bar, that's an implicant. The combination of these two, that's an implicant, okay, which is A bar, C, D. the combination of these two, which is A bar C D bar, is an implicand. The combination of these two is an implicand, which is A bar B bar C. The combination of these two is an implicand, which is A bar B C. The combination of these two is an implicand, which is A bar C. Okay, so my function has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 implicants. Okay? Anything that becomes 1 turns my function to a 1. That's an implicant. A prime implicant. If I have an implicant not covered with a larger implicant, it is called a prime implicant. Well, this is an implicant, but see, this one is covered by a larger one, and therefore the smaller one, the lower one, is not a prime implicant, but the upper one, the bigger one, is a prime implicant. All of these two, these four, this one, okay, let me show them with different colors. This, and this. This, this. You're counting 8. Okay, 4 little ones, 4 that contain 2 mean terms. All of these are completely covered by this. Okay, therefore they are not implicants. Therefore those little ones are not prime implicants, and you only have one prime implicant here, one prime implicant here. Okay, so implicants, anything that can turn a function into a 1 is an implicant. Prime implicant is an implicant that no other implicant can completely cover it. Okay? Essential prime implicant. Essential prime implicant. Okay, let me do an example here. In which I'm going to show you implicants and prime implicants again. Let's say my function is this. This is a prime implicant. This is a prime implicant. This is a prime implicant. Okay? But then the orange one and the green one have at least a 1 that no other prime implicant covers them. They have at least a 1. See, this one has this one and this one that no other prime implicant covers them. This one, the orange one, has this one and this one that no other prime implicant covers them. But look at the white one. The white one has these 2 ones on the left that the orange map covers them. It has 2 ones on the right that the green map covers them. And therefore, the white one is not an essential prime implicant. In this function, I have many implicants. I have 3 prime implicants and I have only 2 essential prime implicants. To come up with a minimal coverage, this is how you go about it. First, you identify all your prime implicants. Okay? Then, among those prime implicants, you identify the essential prime implicants. And then you pick essential prime implicants as what you need, you definitely need, that are essential for implementation of your function. Okay? Essential prime implicants. Then you look, are there other mean terms not covered by the essential prime implicants? If so, then you start covering them using prime implicants only. Okay? So, start with prime implicants, identify essential prime implicants. For minimal coverage, use essential prime implicants. Then look back. Are there mean terms not covered? If there are mean terms that are not covered, then use prime implicants that cover most number of uncovered mean terms. Continue doing so until there are no more uncovered mean terms. Okay? Which makes sense. Let's do this example here. And I have a donker. I have some implicants, prime implicants, essential prime implicants, and all that. Okay, on the left-hand side map, I first identify. I'm not gonna. I can if you want me to. But see here, but I'm gonna erase them. Prime implicant, prime implicant, prime implicant, prime implicant, prime. I'm sorry, implicants. These were implicants. So counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 implicants. Of all of these, you only have 1, 2, 3, and 4 prime implicants. 4 prime implicants because there are no other implicants covering these 4 that I have identified. What do you do with donkers? Treat them as mean terms. Treat them as ones at the beginning. Okay? Now, in this map, try to identify the essential prime implicants. Well, essential prime implicants are those that have at least a 1 not covered by any other prime implicant. Well, look, this one has a 1, this one, not covered by anything else, and therefore that's essential. This one has 1, 2, 3 ones not covered by anything else, so that's also essential. How about this prime implicant? Well, this prime implicant has a 1 on the left hand side that is covered by the by this one, okay, and it has a 1 on the right hand side. I don't care, but for now we treat them as 1 that is covered by this prime implicant. Therefore, this prime implicant is not essential. Neither is this one. Okay? And therefore, the only essential prime implicants are these 2 here. For the minimal coverage, I write these essentials. This is this one. This is this one. Then I look back and then look to see if there are other mean terms not covered by using only essentials. I find that yes, indeed, there is 1 not covered, and I have to cover it. Then I start looking at prime implicants that cover this. I choose those prime implicants that cover the most number of uncovered mean terms. Okay? But there is only 1 uncovered mean term, and taking either this or this will cover it anyway, and therefore I can choose either one of them. And therefore you are seeing that my function is a bar d, a c bar d bar, and then I have b c bar d bar means this one. Or I could do a bar b c bar. Okay, either one would cover this function. Realization is not unique because I had a choice of taking either the prime implicant, this one, or this prime implicant. Okay, that is a good example for implicants, prime implicants, and essential prime implicants.